Hello, everyone. Thank you for joining us today. My name is Katie Emilio, and I'm an engineer in the Professional Development Department at ACI. I'd like to welcome you to today's webinar, Understanding the ACI 56221 Concrete Repair Code webinar series, Part 2. Yesterday, we had Part 1. For continuing education credit, attendance for the entire duration of today's live webinar will earn you a certificate of completion for 2 PDH. Your certificate will be available in ACI University under the Certificates tab within 2 days. And again, for those of you who cannot join us live today, we will have the recording available in ACI University. Please feel free to use your GoToWebinar toolbar to ask questions, and our speaker will be happy to address them at the end of the presentation. ACI is an approved education provider for AIA and ICC, and today's webinar has been approved for 2 learning units. Our course description is as shown on the screen, and it's also available in your handout. Today, we're going to be discussing how to determine the design basis code for rehabilitating an existing concrete project structures. The learning objectives are also there. And now I'd like to take a moment to introduce our speaker for this afternoon, Mike Bartlett. ACI Fellow Mike Bartlett is Professor Emeritus of Civil and Environmental Engineering at the University of Western Ontario in London, Canada. He is a founding member of ACI Committee 562 and has chaired Subcommittee B Loads through all the editions of the standard. He earned his PhD at the University of Alberta, supervised by ACI past President Jim McGregor. His research activities focus on structural reliability, code calibration, and in particular, the assessment of existing buildings and bridges. He is also the chair of CSCE's National History Committee. And with that, I would like to pass it over to Mike to begin today's presentation.
Katie, thanks for that kind introduction. Good morning to those of you in the Pacific and Mountain time zones, and good afternoon to everybody else. This is the part 2 of understanding the ACI 562 concrete repair guide. Keith Kessner gave part 1 yesterday, and I'm following up today, as Katie said, to talk specifically about chapters 4, 5, and 6 of ACI 56221. I want to start also by warmly acknowledging the excellent work of Khalid Nalawi, who prepared the first draft of this presentation deck. Any mistakes or corrections or omissions are my fault, not his. We started yesterday talking about carrying out a preliminary evaluation or preliminary assessment in accordance with section 1.7 of 562. If it was discovered that the structure was adequate and safe, then one would proceed with a repair. But if the structure had a deficiency, then we go through a number of steps that we'll be talking about today. First is selecting the design basis code in accordance with chapter 4. Second is selecting the factored load combinations and strength reduction factors in accordance with chapter 5. And finally, we'd be carrying out an assessment in accordance with chapter 6. So there's the design basis code. We'll be talking about that first. The learning objective for this module, module 3, is to determine the design basis code. So we need to start with some definitions here. I concede that I always find all of the different codes that are defined and described in ACI 562 a little bit confusing. So let's see if we can get them sorted out at the beginning. We can talk about the current building code, and the current building code is the general building code adopted by a jurisdiction that presently regulates new building design and construction. In many jurisdictions in the United States and elsewhere, this is the current edition of ACI 318. We can talk about the original building code, which is the code that was used to design and construct the structure originally. The original building code might be a working stress or allowable stress design based standard. And if a structure has a later addition, then there would be two or more original building codes, one for the original structure and perhaps a different original building code for the addition. And finally, we have the existing building code, which Keith talked about yesterday. It's the code for the assessment, repair, and rehabilitation of existing buildings. In the United States, this is commonly the International Existing Building Code, or IEBC, developed by the International Code Council, ICC. The IEBC provides regulations for evaluating damage and the limit for damage to be repaired using the original building code. As of January 2016, the IEBC had been adopted in approximately 80% of the states. Keith went into some detail yesterday showing us a map. Guam and Puerto Rico. For jurisdictions that have not adopted an edition of the IEBC, that jurisdiction is considered to have no existing building code. In this case, the provisions of Chapter 4 of ACI 562 and any chapters in the current building code that address existing buildings must be met. So first, just to emphasize, what is a design basis code? This is the formal definition. It's the legally adopted code that provides the requirements under which the assessments, repairs, and rehabilitations are designed and constructed. So the design basis code is the rule book for the assessment, repair, and rehabilitation process. We have, as Keith mentioned yesterday, two procedures in ACI 562 for selecting a design basis code. One, which is represented by the string or chain of documents on the left-hand side of this slide, would involve combining parts of ACI 562 with the IEBC to become the design basis code. The other option, represented on the right-hand side of the slide, would be to apply the provisions of Chapter 4 and other parts of 562 without the IEBC to form the design basis code. The engineer or the licensed design professional can always choose to use the current building code for repair, for all damage states, to assess deterioration, to address faulty design or faulty construction. The disadvantage with doing this is that in many instances, the current building code is overly conservative, as Keith was describing yesterday, and may not be cost effective. So the idea with Chapter 4 is that the design basis code criteria for a project can be defined using the requirements set forth in Chapter 4, and this can be used, as we said previously, in conjunction with the IEBC, where the IEBC has jurisdiction. So the rest of our discussion of Chapter 4 today will describe the case where ACI 562 without the IEBC is the design basis code. In other words, the case where the existing building code is not used. Article 421 of 562 states that the design basis criteria of the project is determined based on the results of preliminary assessment as described in 1.8 or the detailed assessment as described in Chapter 6 using the requirements of this chapter. The design basis code must be used consistently for all assessment, repair, and rehabilitation design work or areas of the structure. Structures that were constructed under previously adopted codes or before the adoption of a building code may not satisfy all current building code requirements. Chapter 4 contains specific requirements that determine if existing structures should be repaired or rehabilitated to satisfy the requirements of the original or current building code whichever serves as the design basis code. Local ordinances may also require that a structure be rehabilitated to satisfy the current code. What do we use when we're adding new members? For new members, Article 423 of ACI 562 states that ACI 318.19 shall be the design basis code for new members and for connection of new material, new members to the existing structures. So new members, ACI 318, the current building code. What code to use for repairing? For repairs, and I think of repairs as bringing the structure back to a previous capacity, not necessarily strengthening the structure. It's permissible to use the original building code as the design basis criteria for new or supplemental repair elements built integrally with the existing concrete. And so clause 4.2.4 states that the repair detailing shall be the current building code unless specific conditions are satisfied. And so this slide gives the conditions. The existing reinforcement could be designed to the original building code if damage or deterioration to existing reinforcement is addressed. The capacity has to be at least capacity has to be at least equal to the demand using the building code. And if your original building code is an allowable stress design based code, then you need to satisfy the requirements of 453 to use original building code criteria to detail repairs. This is a table that we'll return to on several occasions to help us understand how the rehabilitation category is determined. Distinctions are made between potentially dangerous structural conditions, substantial structural damage, damage less than substantial structural damage, deterioration and faulty construction, and finally, additions, alterations, and change in occupancy. We'll work our way through this table over the next few slides, but the thing to note is that the numbers in the right-hand column of this table are the ACI 562 provision numbers that pertain to these different conditions. Generally speaking, as Keith said yesterday, ACI 562 is used for gravity and lateral wind loads, and ASCE SCI 41 is used for lateral earthquake loading. So let's start with the two cases that are circled in this table. The case of potentially dangerous structural conditions, a classification, by the way, that will likely be renamed in the 2025 edition of ACI 562 to parallel a renaming in the IEBC. The licensed design professional would calculate the strength demand based on the current building code, considering gravity, fluid, soil, and lateral and wind loads, but not seismic loads. The governing load cases are determined using the factored load combinations of ASCE SCI 7. If, as shown on the screen, the factored demand U sub C exceeds the factored resistance phi R sub Cn by 1.5 or more, potentially dangerous conditions are deemed to be present, and the design basis criteria is the current building code. Again, RCN, the current in-place nominal capacity, including the effects of any concrete or steel damage and faulty construction. UC is the demand for the nominal loads using the factored load combinations in ASCE 7. And in that case, the design basis code is the current building code. This slide doesn't actually define phi, but the strength reduction factor, I'm sorry, I'm a Canadian, we call them resistance factors, but I'll try to remember to call phi strength reduction factors. There actually, we'll see two sets of strength reduction factors that could be used when checking this equation that we'll describe when we get to chapter 5. If you have potentially dangerous structural conditions, then the licensed design professional must report unsafe structural conditions to the owner, to the building official, or both. Potential dangerous structural conditions requiring immediate attention are reported to the appropriate authorities, we've just said, and they must be addressed. So, for example, the LDP can consider whether alternate load paths are present to address potential deficiencies, whether the load can redistribute or conceivably limiting the live load to prevent existing members from being overloaded. Alternatively, we could add temporary or permanent secondary supporting members, temporary shoring perhaps, to relieve the overloaded members. So this table just summarizes that the design basis code is required, the conditions where the design basis code is required when potentially dangerous conditions are met. Again, for gravity and wind loads, if the factored ratio of the factored demand to the factored resistance exceeds 1.5, you've got potentially dangerous conditions, and you're going to use the current building code as the design basis code. If your deficiency is due to seismic, then you're going to go to ACI, SCI 41 and 562 to determine how to proceed. That really, ASCE 41 becomes the design basis code. And this slide just repeats that really. The design basis criteria for rehabilitation design and construction of unsafe structures when seismic resistance is the issue is ASCE SCI 41 with a little bit of help from ACI 562. So we're back to this table again. Now let's look at cases where substantial structural damage is present. We can think about substantial structural damage to vertical elements of the lateral force resisting system or to vertical elements of the gravity load resisting system. If there's a reason for the licensed design professional to question the capacity of the structure based on the results of the preliminary assessment, an assessment shall be performed in the work area to determine if substantial structural damage is present. Substantial structural damage in the work shall be assessed using the current building code demands, nominal capacities according to Chapter 6, and strength reduction factors according to 5.3 or 5.4, which again we'll talk about in a few moments. So this slide shows one of the triggers that defines substantial structural damage to a lateral force resisting system. The substantial structural damage to vertical members of the LFRS is deemed to have occurred if in any story the shear or columns of the LFRS are damaged such that the nominal capacity of the structure, the damaged structure, some R sub Cn in any horizontal direction is reduced by more than 33% from its pre-damaged condition, which is sum of the Rn. So if the original total capacity is 50% greater than the capacity accounting for the damage, one has substantial structural damage. And this slide, the highlighted columns in this monolithic frame are part of a lateral load resisting system. And if the sum of the original capacities divided by the sum of the capacities accounting for damage is greater than 1.5, then all of the columns on this particular floor would be deemed to have substantial structural damage. If we're talking about a gravity load system, substantial structural damage due to the vertical elements is deemed to have occurred if, for any wall or column or group of individual vertical members of the GLRS, whose tributary area is more than 30% of the total area of the structure's floor or roof, the damage is such that the total vertical nominal capacity is reduced by more than 20% from its pre-damaged condition. So we have a similar ratio as to the one we were calculating previously, the capacity of the undamaged members divided by the sum of the capacities of the damaged members. And if that ratio exceeds 1.25, then that would be a gravity load resisting system with substantial structural damage. This slide is helping to make that point. It's indicating a region of a gravity load resisting system where the nominal capacity of the columns supporting at least 30% of the area, 30% of the total floor area, have been reduced by at least 20%. So maybe it's not all of the columns on the floor, but it's columns supporting at least 30% of the floor that define the criteria for substantial structural damage. There's a second trigger that defines substantial structural damage and for a gravity load resisting system, and that trigger comes into play when the current building code factored gravity load combination, we're thinking about dead, live, and snow load specifically there. If the demand for that factored gravity load combination to the in-place vertical design capacity of the damaged members is more than 1.33. So again, potentially dangerous. The limit on the ratio on the right-hand side of this equation is 1.5. For substantial structural damage, that limit on the right-hand side of this equation reduces to 1.33. So again, this table summarizes the definitions of substantial structural damage for lateral force resisting systems and for gravity load resisting systems, and the documents used as the design basis codes. If it's a lateral force resisting system subjected to wind, then you're using and you have substantial structural damage, then you're using the current building code demand and supplemented by ACI 562 as the design basis code. If you've got a gravity load system and that's defined by either of those demand and capacity limitations, then the design basis code is going to be the current building code demand superseded again by or supplemented again by the requirements of ACI 562. And if you've got a seismic assessment, then you're going to be using ASCE SEI 41. So back to the table again. This time we'll explore damage less than substantial structural damage and deterioration and faulty construction. And we can think about those categories, either rehabilitation without strengthening, where you're just bringing things back to perhaps a previous strength level, or you can think about either of those categories with strengthening, where you're now making the strength of the rehabilitated element stronger than the previously designed strength was. This is a little busy, but here we've got another table that defines less than substantial structural damage. if you've got a U divided by phi naught RCN exceeding 1.0, here phi naught and U naught are going to be the strength reduction factors and the factored load combinations as determined using the original building code. If the element is unsatisfactory by the original building code, then you have less than substantial structural damage, but new members must comply with the current building code. If you've got deterioration, damage, or faulty construction that doesn't require repair, then you're going to use ACI 562 chapters 7 through 10. There's also clause 4.6, which the LDP may determine that in a preliminary assessment based on engineering judgment and without analysis, you can carry out repairs using the original building code if the historical performance of the structure and physical observation of the structural condition of the members and systems indicates that acceptable behavior precluding evaluation by 4.3 or 4.4. And you have to also show that a review of plans and observation of current structural conditions indicate damage or deterioration of the structure below the level of that requiring evaluation by 4.4 and 4.5. And you must show that modifications for additions, alterations, and changes in occupancy are not planned. In that case, you can apply 4.6. And here, reinforced concrete structures designed using allowable stress design. If your original design code is an allowable stress-based code, then the criteria for less than substantial structural damage is that the demand using the original service loads and load combinations of the original building code, U sub S, if that exceeds R sub A, which is the service load capacity of the structural member, including the effects of damage due to of the concrete and steel and faulty construction determined using the allowable stresses according to the original building code. If the ratio of service demand to service capacity exceeds 1.0, then you have less than substantial structural damage and you must be strengthening to the original building code. And finally, let's talk briefly about alterations, additions, and changes in occupancy, our last trip to this table. So here are the criteria used for alterations. Here are the criteria for additions. Additions change the gravity and lateral load demands on member systems or structures in the work area. And so the demand is determined for the configuration prior to the addition using the original building code loads and load combinations. And it's also checked the configuration with the addition using the current building code loads and load combinations. However, if the demand on gravity, the gravity system increases by more than 5% based on the original building code, then due to the addition, the current building code should be used to design new members in the addition. If the capacity of the existing gravity system or members is decreased, that system or member should be checked using the current building code and strengthened if required. And if the addition impacts existing lateral force resisting seismic systems, go to ACI ASCE 41. If the addition is not independent of the existing lateral force resisting system, you're actually using potentially a combination of the current building code for the gravity load paths and ASCE 41 for the seismic load paths. And there's an exception there. And the exception is that if the condition in the lateral demand based on the new code is less than 10% of the original code, then you can use the original code demand and capacities. That's kind of stated by that equation at the bottom. The demand to capacity ratio with the addition is less than 1.1 times the demand to capacity, the original demand to original capacity ratio without the addition. You can use the original code demand and capacities. So this table summarizes these 4 criteria that we've just discussed. And here's a similar slide. Alterations are treated very similarly to additions. And so we've got a definition. Alterations change the gravity and lateral load demands of member systems or structures in the work area of an existing structure. The demand is determined, again, for the configuration prior to the alteration using the original building code loads and load combinations, and determined for the configuration with the addition using the current building code loads and factored load combinations. And we have conditions for alterations that are very similar to those that we've seen already for additions. If the change in the demand, the design forces for gravity loads due to an alteration is more than 5% based on the original building code, you design the alteration using the current building code. If the capacity of an existing gravity system or member is decreased due to an alteration, then you need to verify that the reduced in-place system or member capacity exceeds the current building code demand, and strengthen if it doesn't. If the alteration reduces the lateral load resisting capacity, increases the lateral demand, or creates irregularity, you're going to be using a combination of the current building code for gravity load paths and ACI 41 for seismic load paths. And again, we have this out. If the change in the lateral load demand based on the new code is less than 10% of that, less than 10% greater than that from the original code, you can use the original code demand and capacities. So there's that familiar equation across the bottom. If the new demand using the current code divided by the resistance with the alterations present is less than 1.1 times the original demand divided by the resistance without the alterations present, if you satisfy that equation, you can use the original code demand and capacities. And so there's another table very similar to the one that we saw for additions that summarizes those different cases. A change of occupancy or use. If a change of occupancy or use is changing the demand on the member, the demand is determined using either original building code loads and load combinations or current building code loads and load combinations. If the change in occupancy demand based on the current building code is greater than the demand on those elements using the original building code, the affected elements need to be strengthened using the current building code. So again, demand, the equation at the bottom, the demand using the current code exceeds the demand using the original code, you're going to be strengthening using the current code. If the lateral force resisting system is being evaluated and strengthened, if necessary to meet the basic performance objective for existing buildings, then you're going to be evaluating and rehabilitating the structure per the current building code for gravity load paths and using ACI 41 for the seismic load paths. So we have some examples here. Here, for example, is a repair parking garage girder. The garage was constructed in 1974. You can see there's a little bit of distress there. So the question is, what design basis code should we use to assess and, if necessary, rehabilitate this structure? The original building code in this case is the 1973 municipal code. The current building code in this jurisdiction is the 2013 municipal code. In this jurisdiction, there's no existing building code specified. So because the local jurisdiction has not adopted an existing building code, the design basis code will be determined in accordance with ACI 562 Chapter 4. The preliminary evaluation was performed. It was determined that the structure is in compliance with the version of ACI 318 referenced in the original building code. The evaluation also determined that the structure was safe. Therefore, the repairs could be designed in accordance with the version of ACI 318 used for the original construction. That would be ACI 318-71 and ACI 562. Here's another example. This is a 300 square foot train station facility constructed in the 1920s. Until 1971, the train deck included train tracks and loading platforms. In 2010, the train deck was reconfigured into a multimodal transportation hub servicing light rail commuter trains and buses. Major alterations were performed, and the facility is listed on the National Register of Historic Places. What design basis code should be used to assess and, if necessary, rehabilitate this structure? The original building code would have been the proposed standard building regulation for the use of reinforced concrete, ACI 1910, with Chicago rulings of 1915 for flat slab design. The current building code is the 2009 International Building Code, which refers to ACI 31808. There's no existing building code in this jurisdiction. The local jurisdiction has not adopted probably the 2009 edition of the IEBC. The work classification was considered a level. So yes, because there's no existing building code, we're going to use Chapter 4 of ACI 562 as the repair code. The design basis code, it's determined that more than 50% of the aggregate building was planned for major renovations. And so the design basis code is the 2009 International Building Code. As the structure is on the National Register of Historic Places, the licensed design professional has to consider the Secretary of the Interior's standards for the treatments of historic properties. And the provisions of the section 3409 of the historic building provisions relating to the construction, repair, alteration, addition, restoration and movement of structures, and the change of occupancy shall not be mandatory for historic buildings where such buildings are judged by the building official not to constitute a distinct life safety hazard. So that's a mouthful. A Canadian giving example applications for American heritage structures is a kind of funny place to be in. Anyway, hopefully that's clear. Hopefully, if there's no, you're recognizing that if there's no specified international existing building code, then you're using Chapter 4 of ACI 562 and the different classifications of damage there to determine the design basis code to use. So now that we've got a design basis code, and we're assuming that 562 is the design basis code or part of the design basis code, then the next thing to do is to look at loads. Loads, factored load combinations, and resistance factors that are given in Chapter 5 of 562. A couple of learning objectives here. First, we want to emphasize that the mixing of load combination and strength reduction factors from one code and from different codes is not permitted. And we also want to point out that in ACI 562, there are two unique sets of strength reduction factors. So if ACI 562 is the design basis code, the factored load combinations, load factors, and strength reduction factors of Chapter 5 are used in the assessment of the existing structure and the design of any rehabilitation where such design is necessary. Load factors, as already stated, it's not permitted to use load factors and load combinations from the original building code with strength reduction factors from the current building code. This would clearly be unsafe, for example, if you were taking load factors from or load combinations from an allowable stress design-based code and comparing them to resistances at ultimate strength from the current building code. In general, calibrations are carried out to make sure that the factored load combinations in a particular edition of a code, when combined with the strength reduction factors specified in that particular edition, the calibration is ensuring that the levels of reliability that are achieved are acceptable, that you're getting the desired safety. And if you try mixing those, you're going to get into trouble and you may not achieve the desired safety. And the converse is also true. You don't want to be using load factors and load combinations from the current building code with strength reduction factors from the original building code. What loading should you be using during repair? Well, you need to think about that loading because you're going to be using that to define the shoring and temporary support requirements. If the building is going to be, or I should probably more accurately say the work area, is going to be occupied during the repair, then the loads are per the current building code, ACI SEI 7. If the structure is, or any portion of the structure where the work is performed, is unoccupied during the construction period, then less stringent temporary design loads could be specified using ASCE SEI 37. And if you've got seismic loading, you're going to be going to ASCE SEI 37 and 41. These provisions permit the less stringent loads in ASCE SEI 37 to be applied for the construction access only case. I'm sure you're familiar with this fundamental design philosophy in strength design, which says that the design strength shall be greater than or equal to the required strength. So the left-hand side of the equation is the strength reduction factor phi multiplied by the nominal resistance or strength R sub n, and the right-hand side is the demand U from the factored load combinations. Chapter 5 provides two sets of strength reduction factors. The more stringent values, shown in the center column, apply when designing rehabilitation or when conducting an assessment using material properties and member dimensions that have not been confirmed in the field. If you have done field work to obtain material properties and confirmed as-built member dimensions and reinforcement locations, if you verified those as defined in Chapter 6 of 562, the strength reduction factor shown in the right-hand column may be used. If you're determining material properties from contract documents or based on original construction dates, then the strength reduction factors to use are the more conservative ones in the center column. Chapter 5 also provides a couple of supplemental factored load combinations that apply to external reinforcing systems susceptible to damage and apply to structures that have experienced a fire event. So let's talk about the first case. If we've got external reinforcing systems that are susceptible to damage, the concern here is that damage might occur and that damage might not be noted for some time. And we want to make sure the structure has sufficient capacity not to be unsafe for that period of time that it takes to identify that damage has occurred and repair the damage. The provisions are as shown here. For rehabilitation achieved with external reinforcing systems that are susceptible to damage by vandalism or impact, the required strength of the structure without that internal reinforcement shall satisfy these two factored load combinations. So again, here we're intending to minimize the risk of overload or damage due to the existing unstrengthened member in the case where the damaged external reinforcing system has not been repaired. This would give the owner time to be alerted of the damage and allow the structure to remain in service until the damaged external reinforcing system is repaired. In those two equations, you can see that you're taking a companion action live load condition for this case with a reduced live load factor of 0.5 for the first case or 0.75 for the second case. If the applied live load has a high likelihood of being sustained, books in a library are the obvious example there, for example, then the live load factor in these two equations should be increased to 1.0. The other special load combination that's specified in Chapter 5 concerns fire resistance. And so there are a couple of slides here that Khaled has grabbed from ACI 216 to talk a little bit about fire and fire resistance. And it's strongly recommended that you look at ACI 216 for more information about this. So fire resistance depends on a duration of fire exposure and during which the member can support a fire load without exceeding predefined failure criteria. So let's start with the fire. The graph shows the increase in temperature as specified by an ASTM standard with the time in minutes for this particular fire. The fire is beneath the member that we're worried about. So this figure shows how the heat of the fire is penetrating the member with time. And if I click again, we're worried particularly about the temperature of the reinforcing steel during the fire. Steel loses its stiffness and yield strength as its temperature increases. And so the yellow curve on this figure shows the variation of reinforcing steel temperature with time for the fire defined by the red curve. You can see that at a time of 120 minutes, the temperature in the fire is around 1,000 degrees Celsius, and the temperature of the reinforcing steel is about 500 degrees Celsius. So knowing something from 216 about the reduced properties of steel at elevated temperatures, we can create this third graph, which is showing on the right-hand axis the ratio of the moment capacity accounted for the elevated temperature of the steel to the original moment capacity before the fires occurred. And as you can see, it can drop off quite markedly. If we have a 2-hour fire, then as I said before, the temperature of the steel is going to approach 500 degrees Celsius. And the capacity, there's a line that's missing that should come out here, is approximately half of the original moment capacity. So here we're going to have another figure from 216.1, which is showing the reduction of the reinforcing and pre-stressing steel strengths with temperature. As the temperature increases, for temperatures greater than 300 degrees Celsius, the yield and tensile strength of the steel reduces markedly for reinforcing steels, and it reduces at even a higher rate of strength degradation for pre-stressing steels. Concrete is slightly different. Again, we've got a strength ratio, the compressive strength of concrete under fire conditions compared to the strength of that same concrete under ambient conditions. And there's very little impact until the temperature of the fire or the temperature of the concrete exceeds about 500 degrees Celsius, and then the concrete compressive strength deteriorates fairly significantly at higher temperatures. So Chapter 5 provides this requirement, this additional factored load combination, which is the minimum strength during a fire event without external reinforcement. And so again, we've got with that equation, the idea that during the fire event is a rare event, so the companion action, live loads or snow loads, that would be the magnitude of transient load acting during that short period of time while the fire is taking place, are not the full specified loads, but something less than that. So we have got a 0.5 factor applied to the live load and a 0.2 factor applied to the snow load. Here we're using a strength reduction factor of 1.0 for this case, and we're using 0.9 in conditions where the dead load is helping us, counteracting the live or the snow load effect, or we'd be using a factor of 1.2 on the dead load when the dead load is in addition to making the live load effect or the snow load effect worse. Again, if we've got sustained live loads, the 0.5 in this equation becomes a 1.0. And the other thing to observe about this equation is that this equation is really intended to check an existing structure that has been subjected to a fire and decide whether strength deficiency exists such that action has to be taken to probably limit the live load on the structure. We're going to calculate the resistance based on reduced steel and concrete strengths based on the estimated temperature of the steel and concrete during the fire. So this is starting to show things. Here we've got a structure, a reinforced concrete beam that under ambient conditions has to carry a bending moment, a factored moment of 1.2 dead load plus 1.6 live load. When the fire occurs, the capacity of the steel and concrete is reduced. And so we've got reduced nominal moment capacity during the fire. And as long as that capacity is less than a demand of 1.2 D and 0.5 L, or 1.2 D and 1.0 L if the live load is sustained, we're saying that has sufficient capacity and we don't have to take extraordinary measures to limit, say, the live load on that particular damaged element. So we've got an example here, and the purpose of this example is to see how we might want to strengthen a structure using externally bonded reinforcement. And we also want to be able to go back and make sure, given that externally bonded reinforcement is susceptible to damage, we want to make sure that the unreinforced capacity of the unreinforced structure still meets the requirements of Chapter 5. So there's a ton of information on this slide. We've got 5 bays of structure. There are drop panels there. We've got known existing reinforcement in both dimensions. We've got effective depths of that reinforcement. We've got the self-weight of the 6-inch slab and the drop panels, plus we've got a superimposed dead load of 10 PSF and a specified live load of 40 PSF. Material properties are shown on this slide. The concrete compressive strength is 3,000 PSI. It's an older structure, so the minimum specified reinforcing steel strength is 40,000 PSI. And we're going to be checking for a load combination of 1.2 dead plus 1.6 live loads. The slab is modeled using a software program, and the program is accounting for varying slab thicknesses at the drop panel and between the drop panels. It's accounting for the varying loading patterns of live load that can occur. It's a two-way slab system, and we've got 30-inch diameter interior columns and rectangular exterior columns, and the drop is 2 inches below the slabs. So there's one of the loading patterns that we're going to be considering with live load on both spans. As I dimly remember ACI 318, I think you also need to consider 75% live load pattern loading with 75% live load on one span only. So the loading scenarios are shown here for the self-weight and superimposed dead load and live load. We can calculate typical dead load moments of 39 kip feet and live load moments of 20 kip feet. This is the structural analysis output showing the moments in the column and middle strips in both directions. So again, bay lines 5 and 6 between column lines E and J4. And this is a slightly busy slide, but taking it all, the really key things are the quantities that are shown on the right-hand sides of these tables. So, for example, the first row of data shows that in slab strip G56, where there's a 2 1/8 inch drop panel present, the factored demand is 75 foot kips, and for the given reinforcement and moment arm, the factored capacity is only 68 foot kips. So that's deficient, and we're going to have to reinforce that region to increase the moment capacity. And you can see that there are 1, 2, 3, 4, 5 different places where the top reinforcement is insufficient or the bottom reinforcement is insufficient. And there are another couple of places that are shown by the dashed rectangular regions where the capacities provided by the existing bottom reinforcement are nominal compared to the factored demands. Okay, so we can do our repairs, that's fine. But the next step, we have to make sure that the structure without any reinforcement has sufficient capacity. And for non-mechanically bonded external reinforcement and all FRP systems, the required strength of the structure without external reinforcement shall satisfy those two equations that we saw earlier. This is one of them. We want to check the minimum required strength. In this case, the product of the original resistance factor and the original moment capacity without considering the additional bonded reinforcement is 68 foot kips. And we're going to be comparing that with 1.1 times the dead load plus 0.75 times the live load. And those two together combine to 58 foot kips. And so the capacity of the unreinforced member is greater than the capacity required to meet that reduced factor demand. And we'd say that this is okay. So because this condition is satisfied, external non-mechanical strengthening may be used. So that's most of chapter 5. Let's have a quick look at chapter 6 on assessment. The learning objectives here are first to determine material properties to use for assessment. Second, to understand the different destructive and non-destructive testing methods used for evaluation. And we need to think a little bit about performing the assessment process. There is a ton of material on non-destructive testing methods available in ACI literature, particularly ACI 228.2. And rather than spend a lot of time talking about that today, I'll just point you to 228.2, but we'll mention it briefly. Okay, so you need to perform a structural assessment if potentially dangerous structural conditions exist. You need to perform a structural assessment if the capacity of the structure is questionable. And Khaled dug up these two pretty vivid examples of cases where a structural assessment would need to be performed. What is an assessment? Well, structural assessment is a process of investigating by systematically collecting information to quantify the in-place condition of the structure, evaluating this information to make informed decisions, detailing the findings, and making recommendations, including developing rehabilitation strategies as necessary. So assessment involves defining or establishing the in-place condition of the structure in the work area, including the environment, geometry, material strengths, bar sizes, and placement locations are particularly important, and accounting for any signs of distress. The evaluation considers the causes of distress, the goals of the rehabilitation, and perhaps identifies criteria for selecting rehabilitation solutions. And finally, you're going to come up with appropriate rehabilitation strategies. In assessing the in-place condition, there are several tools to consider. Again, Keith talked about a number of these yesterday. Basically, you're trying to get information from wherever it can be found. So you're going to be reviewing available documentation. You're almost certainly going to be visiting the structure to carry out a visual survey. You're going to be doing destructive and non-destructive testing to sample materials, and you may be carrying out other laboratory evaluations to assess deterioration or corrosion-related quantities or features that may be present in the structure that you're assessing. The flow diagram is shown here, shows how material properties are selected to carry out an assessment. The first thing is to make a decision about whether material deterioration or distress has occurred. If it's present, then you're going to have to do physical testing to quantify the extent of that deterioration or distress. If there's no distress, then the next check is to see if you have existing contract documents that list material properties. If you have such documents, then you would use the properties specified in those documents as material properties, and you might augment that information with physical testing. If you don't have existing contract documents, or the contract documents don't specify material properties, then you'd be using, following the left-hand most branch, you'd be using material properties that were historical material properties based on the date of construction of the element that you're assessing, and you would perhaps be augmenting those with physical testing as well. So this slide details the first option a little bit more. The material properties provided in original construction test reports or material test reports shall be permitted to be used, there's code language, unless deterioration that affects the performance has occurred. If you're going to use historical data based on the date of construction, you'd probably be doing that if you don't have existing documents that has material strength data in it. Then the engineer can refer back to historical data that's included in the 3 tables listed there in 562. These data are intentionally conservative, and so they can be used for a preliminary check, but if the structure is found to be deficient using material properties from these tables, then it would be usually typical to try to get more accurate material properties and carry out an analysis and an assessment using those revised, probably field measured material properties. You can be getting those material properties in the field using destructive or non-destructive methods. So let's look at these historical data for a minute. This is a reproduction, slightly simplified, of table 631A, which gives the default compressive strength of structural concrete. The time frame in the left-hand column of the table is the date of construction of the structure that's being investigated. And you can see we have different compressive strengths specified for the different elements of the structure constructed during these different time frames. A measure of conservatism it'd be to observe that certainly in the present day, the minimum concrete strength used for columns is often 5,000 PSI. And so the value of 3,000 PSI that you'd get from the bottom right-hand corner entry of this table is very conservative. But if you don't have better information, starting with this conservative information is the way to go. Here's the table with historical reinforcing steel yield strengths. The entries marked X indicate that a particular grade was available during a particular time period. For example, grade 33 structural steel with a minimum yield strength of 33,000 PSI and a minimum tensile strength of 55,000 PSI was available between 1911 and 1959, but it wasn't available after 1966. If the actual grade is unknown, then the structural grade would be assumed as it is, well, let me try that again. If you don't know the grade, then you go into this table and you take the worst grade for the date of construction that you've got. So if the date of construction was between 1911 and 1959, then the worst case would be grade 33 material. It could be grade 65 or better. but you'd be taking the yield strength and minimum tensile strength of 33 KSI and 55 KSI for the grade 33 material. Talking a little bit about testing methods, destructive and non-destructive testing methods are used to obtain in-place mechanical properties of materials and member properties, and they're to be in accordance with section 6.4. For in-place testing, the locations and numbers of material samples shall be defined to characterize the materials. The number of samples shall be determined as part of that evaluation process. And really the objective is to obtain reliable information to assist in the evaluation of an existing structure, taking advantage of methods that are non-destructive or methods that involve local surface damage only. So we've got some fairly busy tables here. If we think about testing methods for material properties, the left-hand column gives different material properties that can be tested, and the right-hand column gives primary and secondary methods for testing those properties. Probably the primary method for getting a compressive strength is to carry out core testing, but there are secondary penetration resistance tests, for example, that correlate to core strengths. You can get relative core strengths from a number of non-destructive test methods, including rebound hammers, penetration resistance. You've got direct splitting tensile strength tests to calculate direct tensile strengths. You can use impact echo or GPR to get element thicknesses, and GPR is often used to identify bar sizes and locations. And then there are a bunch of durability tests that are listed here as well that can be used. If you're trying to quantify damage and deterioration, then you're interested in things like the corrosion state of the bars, the steel area reduction, the presence of delaminations or near surface defects, the presence of internal defects, fire damage. Then there are a number of primary and secondary test methods listed on this slide to do that. And again, reference to ACI A228.2 as the source of a great deal more information about these methods. This slide lists the various non-destructive methods for in-place materials. The rebound hammer, penetration resistance, and pull-off tests require calibration using compressive core strength tests. The correlation between the compressive strength and the result of those non-destructive tests depends on things like the aggregate in the concrete. And so ACI 562 requires that correlations be made between core strengths and the strengths obtained using these various non-destructive tests to get reasonable values to use. Stress and NDT tests based on stress wave methods are typically used to determine the presence of cracking, honeycombing, voids, delaminations, and deteriorations. They can also be used to determine member thickness. Bar location, perhaps ground penetrating radar, is now the most commonly used method to locate reinforcing bars. And finally, there are many useful NDT methods available to quantify the condition of concrete members and so assess the durability of the concrete in the structure. Useful references are given here. ACI 228.2 is the report on non-destructive test methods for evaluation of concrete and structures. And the two reports from ACI 222, corrosion of metals in concrete, are excellent sources of information to support this part of the assessment process. Let's talk about some destructive methods momentarily. Chapter 6 does permit obtaining samples of the in-place materials of structures being evaluated and constructing destructive tests to determine the compressive strength of concrete, the yield and ultimate tensile strength of reinforcing, and other steels. And the various clauses or sections of the code that specify these tests are listed here. The concrete compressive strength can be determined by core tests or a combination of cores and using site-specific non-destructive testing. The non-destructive testing to evaluate the in-place strength of concrete shall be permitted only if a valid correlation is established with core sample compressive strength test results and non-destructive test results from the concrete in the structure that you're looking at. It's not permitted to quantify compressive concrete strengths by NDT alone without core tests. Here are a few criteria from ASTM C42 and ASTM C623. We need cores taken from sound concrete. We need locating bars before the coring, and we do need a minimum of 2 cores to constitute a core test. I was amused to see this slide appear in Khaled's deck because it summarizes research that I reported as part of my PhD thesis sometime back in the last millennium. I think things must have changed because the people doing core testing weren't nearly as neat and tidy as the individual pictured here. During placement, concrete, the self-weight of the plastic concrete actually consolidates the concrete in the lower portions of a column or a wall. So if you're coring a column or a wall, you should take the core from the middle half of the column. As you work your way towards the top of the column, where that consolidation pressure isn't available, the concrete strength drops by, say, up to 15%. And if you're coring near the bottom of the wall, where that consolidation pressure is the greatest, then the compressive strength can be higher by 10%. A key word here is typically. There are significant variations from the 10 and 15%, but coring from the mid-height half of a column or wall is probably the best thing to do. This is a slightly busy slide, but it makes a very important point that it's unsafe to use core strength test results directly in conventional strength equations. And instead, ACI 562 specifies, based on the alternate method that's given in ACI 214.4R, a way of calculating an equivalent to specified concrete compressive strength using this equation shown. So you're going to calculate the mean core strength, F prime C, which FC bar, which you may have modified to account for the diameter and moisture condition of the core. The quantity in parentheses includes the coefficient of variation of the core strengths. Coefficient of variation is the standard deviation divided by the mean. It includes the number of core strength tests N, and it includes a coefficient of variation modification factor, K sub C. The idea with K sub C is that if you've got a small number of cores, you may not accurately estimate the coefficient of variation of the true population from that small size sample, so you have to be conservative and increase that value. And you can see that as you go from N of 2 to N of 20, your K sub C value reduces markedly from a number like 2.4 to a number like 1.03. So the quantity that's in parentheses is actually giving you roughly the 90% fractile of the mean, the lower 10% fractile of the mean in-place strength, and you're multiplying that by a factor of 0.9 to account for the within structure variability of the concrete. So just using the mean core strength FC bar in a resistance equation would be quite unsafe, because the actual equivalent concrete specified compressive strength would be a number less than 90% of that mean core strength. And as we've said before, you can use NDT, but only if statistical correlations with core test results can be established. So there are a couple of popular NDT devices. For steel reinforcement, it's inconvenient that it's fairly easy to find out about concrete strengths, but many resistances are actually quite insensitive to the concrete strength. So whatever you can find out about the steel reinforcement, the bar sizes, the number of bars, the locations of the bars, the effective depths, those are all very useful pieces of information in an evaluation. This is a useful graphic just to remind not to take samples where they're likely to be highly stressed. So you're going to take longitudinal bars, ideally near an inflection point where the stresses are low, and you're probably going to try and do stirrups near midspan, again where the stresses are low. For walls and slabs, the samples on the longitudinal bars should at least be separated by a development length, so you're not over weakening a particular region of the beam. 562 doesn't specify how many samples should be taken from a member, but 364.1R suggests the criteria shown here, that if your span is less than 25 feet or the loaded area is less than 625 feet, you would take at least one sample from a longitudinal bar, and if you have a higher span or a higher loaded area, you would take more samples. Again, you can't use the average yield strength directly in a resistance equation. You have to calculate an equivalent to specify yield strength. And this equation is intended to give an estimate of the lower 10% fractile of the yield strength in the sample set that you have. The 3,500 number, that's 3,500 PSI in the parentheses, accounts for the reduced yield strength that occurs when a piece of steel is loaded statically compared to the higher yield strength that would be observed at the test loading rate. And we again have the coefficient of variation of the test strengths in there. Higher coefficients of variation will give you lower equivalent to specified test strengths. And we've got, again, a steel coefficient of variation modification factor for small sample sizes. So again, it's kind of up to the licensed design professional to figure out how to optimize selecting a sample size to balance the costs of the obtaining and testing samples with the conservatism associated with small test results. I guess the thing I might observe is that typically steel reinforcing bars, if they're the same size in a structure, they've probably come from the same heat of steel. So the mean yield strength may not be a whole lot higher than is assumed in the calibration for new construction. But because they're all from one heat, the coefficient of variation is often much, much smaller than it is for sort of design where steel bars from all heats have to be considered. The concrete strengths, especially core strengths, can be at least as variable as that assumed for new construction, but often the compressive strengths are markedly higher than the minimum specified values, especially if the concrete is old, large grain cement particles, which continue to hydrate with time. We're just about there. Pre-stressed reinforcement. Boy, be careful removing pre-stressing steel reinforcement. Its testing requirements are given in ASTM A1061. There is some historical data offered in 562 and elsewhere about pre-stressing steels. And unbonded reinforcement, as I'm sure people are aware, is potentially quite dangerous stuff. So you want to be very careful trying to sample that. The remainder of Chapter 6 includes short sections on means to analyze existing structures, on evaluating the serviceability of existing structures. Sometimes it's necessary to carry out a serviceability assessment. Often it is not. Carrying out structural analysis for repair design, that really focuses on how, when you're designing a repair, you're probably partially disassembling the structure and reassembling the structure. And so at each step of the repair, the safety of the structure has got to be assured. And there's a section on structural evaluation by load testing, which is essentially ACI, the provisions given in ACI 437.1. So that's mostly it. We have selected a design basis code using the provisions of Chapter 4 of ACI 562. We've computed loads and factored load combinations and strength reduction factors using Chapter 5, and we've carried out an assessment using Chapter 6. So with that, I'll pause and see if we have any questions.
Okay, thank you, Mike. Yes, we do have some questions. All right, our first question, I think this is from slides 56 and 55 when you were talking about the historic building example. And the question is, for the historic building example where you are determining the design basis code, where is the requirement regarding more than 50% of the building is affected, which triggered the use of the current building code?
Okay, so let me first go back to that slide. Okay, so presumably we're talking about this line right here, and I haven't actually, this example is not my example. The notes that I have say that the work classification was considered a level 3 alteration, given that more than 50% of the aggregate building was planned for major renovations. And I'm assuming that that's probably part of the 2009 IBC. But if somebody wants to correct me on that, I am quite willing to be corrected, because I'm just reading this off my script.
I do have a follow-up question to that for you.
Okay.
If you don't have experience with identifying the design basis code for use on a project, where can you go for guidance?
So again, I would start with chapters 1 and 4 of ACI 562. Actually, sections 1.7 and 1.8 describe quite clearly, as Keith Kessner said yesterday, about what you're supposed to be doing if you've got the jurisdiction that you're working in has specified an international existing building code or not. And then based on that, you're going to be coming to Chapter 4, and if there's no existing if there's no existing building code specified, then you're going to be basing the design basis code on either the original building code or the current building code, depending on the status of the structure that you're assessing. So if you've got potentially dangerous structural damage, for example, Chapter 4 tells you to use the current building code. If you've got less than substantial structural damage, Chapter 4 tells you to use or allows you to use, is a better word, the original building code. If you're Keith made reference to a very useful document yesterday that gives examples. So ACI and the Concrete Repair Institute have prepared a guideline with example calculations on the use of 562, and I would suggest that that would be a very useful document to have with 562 to learn more about that question.
Okay, our next question, you were talking a bit about fire resistance, and this question is it true that the heating of steel to a temperature that does not produce yield under the heated condition does not significantly reduce the strength of the steel upon return to ambient conditions, but the same is not true for concrete?
Yeah, that's an interesting question. I'm not really a fire expert. I do know that depending on the kind of aggregate you have in the concrete, you can decide if the concrete aggregate has changed color during the fire. That's a sign that the aggregate has to be removed. And so that would be addressing the second part of the question that says the concrete can't recover its strength after the fire has occurred. But I don't know if steel can return to its original yield strength if it has not yielded at a lower yield strength during the fire.
All right, our next question. Do equations 6.4.3.1 and 6.4.6 appear in any other ACI standard, code, or guideline document?
6431 and 646. Okay,
Yeah.
so yes, a version of 6431 appears in 214.4R, and the version that appears in ACI 562 is actually a slightly simplified version of what's shown in 6.4.3.1. And Keith yesterday mentioned a series of Concrete International articles that describe the derivation and development of ACI 562. And one of those articles was written by me, and it actually draws the line between what's in 214.4R and what's in 562. The other equation for equivalent specified strength of reinforcement does not appear in any other ACI documents, but both of those equations have been around for quite some time. They've been used in the Canadian Highway Bridge Design Code since the year 2000 to assess the in-place strengths of concretes and reinforcing steels. And in fact, there's a similar equation to 6.4.6 that's used to assess coupon results for structural steels as well. So one equation is in a version, the 6431 is a simplification of an equation that's in 214.4R, and the other equation is not in other ACI documents, but has been used elsewhere.
Okay, thank you. We have another question that's specific Well, they mentioned slide 26, so I don't know if you want to go to slide 26 or not.
Sure, let's see if I can figure that out.
Okay.
Yep.
And the question is, on slide 26, when should an engineer deem a structure to be unsafe? Does that change from a safe structure to an unsafe structure? Does that occur between damage less than substantial and substantial structural damage? Or does the structure become unsafe between substantial structural damage and potentially dangerous structural condition?
So I think actually all of these conditions are unsafe structures, and the question is, what are you going to do about it? So Keith yesterday described carrying out a preliminary assessment, and if the factor demands calculated using the current code exceed the factored resistance, then you have a condition where you don't, you have a condition of unsafe. And so the various things that are shown here are providing measures for deciding how you're going to deal with that unsafe condition, and in particular, what rehabilitation category you're going to be using to address the deficiency. And so basically, as you go from potentially dangerous structural conditions to damage less than substantial damage, the design basis code requirements become less onerous. You're allowed to use the original building code more frequently to design the rehabilitation or repair than the current building code.
Okay, our next question is, does ACI 562 have any requirements for mechanical bonding when the result of delamination of the repair may lead to failure?
So I'm going to pass on that one. The short answer is yes, quite a few requirements, and I'm quite sure that the next webinar in this series will be addressing that explicitly. So rather than confuse people with a bad answer now, I'd invite the person who asked the question to come back on Monday next week and take in that webinar.
Fantastic. All right, another question we have for you. Is there a code for bridge repair?
That's a very interesting question. First of all, I'm a little bit handcuffed because I don't know the AASHTO standard all that well. There is, as part of the Canadian Highway Bridge Design Code, section 15 on rehabilitation, and it gives a few interesting things. It gives reduced design traffic loads for rehabilitation that can be applied in certain circumstances. It gives a great long list of things that you need to think about when you're carrying out a rehabilitation. I guess I've sat on the committee that writes that for quite some time, and I think one of the things that that committee's always been trying to do, and I think that's sort of a little bit part of 562 as well, is not to tie the rehabilitation designers' hands too tightly. That with prescriptive requirements, that the optimal rehabilitation is something that depends on a number of factors that tend to be very site specific. What sort of damage are you looking at anyway? How busy is the road that the bridge is the bridge essential to providing life critical services? Is it on the way to a hospital or something like that? And so it is the only standard that I'm aware of that addresses bridge repair and rehabilitation is that one. There are a number of guidelines that are provided by provincial highways ministries that get into the nuts and bolts of how to do rehabilitation. You know, best practices if you're doing partial bridge deck repairs or something like that. But apart from that, I'm not really aware of anything. And as I don't think ACI's got a bridge rehabilitation committee. It's got a bridge design committee and it's got a bridge evaluation committee, but I don't think it has a bridge rehabilitation committee.
If I can build on your answer a little bit, I phoned a friend. We all know Khaled. He recommended that, you know, Keith did mention in one of the slides yesterday, 562 can be used for all concrete structures. So we could apply it to bridges, and we should have a few guides that address bridge repair as well.
Yeah, so your friend is technically right. I would say additional work really needs to be done to apply 562 to bridge rehabilitation, in the sense that, I mean, the distinctions between current codes and original codes are probably valid, but the loading conditions for bridges are really quite different animals than they are for buildings. And I don't know that the load factors and load combinations defined in Chapter 5 of 562 could be readily used for bridges. So I think there's good information in 562 that could be applied to bridges, but personally I'd be finding it difficult to adopt it wholeheartedly for bridges.
Okay. We do have another question. It's a little bit lengthy. Are you ready?
Okay. Sure.
So the attendee says, I think there is a conceptual problem. ASCE 41-17, or now the ASCE 41-23, is not intended for buildings with damage caused by earthquakes. See commentary in Chapter 1. Furthermore, ASCE 41-17 and 23 refer to FEMA 306 to 308 for concrete buildings with seismic damages. ASCE 41 is for evaluation and retrofit of buildings without damage. So I'm not really sure how we're supposed to use the structural analysis for a damaged building with the ASCE 7, which is also intended for a new structure, to a damaged structure which requires nonlinear modeling of the damaged elements. How do you propose to do the structural analysis on damaged structures if it is nonlinearly damaged? And how do we model the damaged elements such as floors, etc.?
So that's a really good question, and I'm just, maybe the thing to do, please, is that if we can save that question and share it with others, we can get an answer to it. I'm not, unfortunately, based in the United States, and so I've never used ASCE 41, and while the question sounds entirely credible to me, I just am not placed to be able to answer it. I'm sorry, but we'll try and get an answer for that.
Okay, we do have a couple more questions. This question is, it's great that the code has a method to determine the design basis code so that a structure does not need to be strengthened to the current code level if determined so. But what if the building official still insists on strengthening to the current building code? What other options does the engineer have in that type of situation?
Yeah, so that's a good question too. And I think I'm going to borrow some comments that Keith made yesterday, because I think that's the answer to the question. And the answer really is that one of the reasons for creating 562 was to specifically address that circumstance and to give the engineer who wants to do repairs using the original building code some ammunition and some justification to go to a building official and say, this is permitted by ACI 562. And incidentally, as Keith noted yesterday, I hope I'm getting these numbers right, but I'm pretty sure that the 2025 edition of the IEBC will name 562 as a reference. And so that would make the engineer saying, I'm designing using 562, would give that individual even more credibility in having the discussion with the building official about why this was the appropriate way to go. So again, I'm hampered a little bit by being a Canadian and not having to work with building officials very frequently, and certainly building officials have a lot of clout. But a purpose of 562 is to give the engineer some ammunition to be able to justify not having to repair or rehabilitate to the current code, but to rehabilitate or repair to the original building code.
Okay, thank you, Mike. And I do think Keith mentioned it would be an IEBC 24. I think that's what he said.
24, that sounds right. Good, thank you.
You're welcome. So we have another question. When you talked about core testing location, you were explaining like where on the column or wall to take it based on, the pressure from the concrete in there. But you didn't talk about the size of the cores. And so this question focuses on that. It's what is a minimum size core that can be extracted out of a concrete member? Is it 4x8 or would something smaller like a 2x4 or 3x6 inch nominal cylinder be acceptable? And if that is acceptable, how would we correlate their strength to a 4x8 or 6x12?
Yeah, so that's a very good question. We'll start the answer by saying that the provisions in 562 and particularly the equation 6.4.3.1 that we showed in this presentation, those only pertain to cores that are 4 inches diameter or 6 inches diameter. If you have a 3-inch diameter core or a small core, then you're probably going to ACI 214.4R for assistance. Again, reflecting on now very ancient PhD research, the difference in strengths between 4-inch diameter cores and 6-inch diameter cores isn't all that big in practice. The difference between 2-inch diameter cores and 4 or 6-inch diameter cores on average isn't all that big, but it's a lot more variable. And so I'm pretty sure 214.4 recommends that if you're using smaller cores, that you try to establish a correlation between the small core that you're using and a larger, more conventional core for the concrete that you're actually working with. So 562 doesn't specify a minimum core size, but it does say that the provisions that it provides only apply when you've got tests of 4-inch or 6-inch diameter cores.
Okay, want to thank you again for taking the time to talk with our audience and walk through information on the design basis code and load combinations and strength reduction factors. Please visit ACI University for our upcoming live webinar topics. And as you are aware, part 3 of the 562 webinar series will continue next week on Monday, September 25th. We look forward to having David Tepke, and he's going to be reviewing repair methods and real-world case studies. So ACI does also offer learning in an on-demand format, and that's available through ACI University. That concludes today's presentation. We hope you'll choose to join us for future learning opportunities. Have a wonderful afternoon. Again, thank you, Mike.
Thanks. Bye for now.